All right. Thanks, everyone, for coming back from the break promptly. I know it's hard getting away from the conversations. We're going to have more today. This next talk, I'm really excited to introduce. What do the posteriors of probabilistic programs look like? Alex Lev is going to be giving this talk. So with that, I'll turn it over to him.
Great, thank you. And hi, everyone. I'm Alex Lev. And today I'll be presenting some joint work with Mathieu Huot, my advisor Vikash Mansinghka, and Mathieu's advisor Sam Staton. So I don't think I need to convince anyone in this room that probabilistic programs are a very expressive way of writing down probability distributions and other measures. Just by incorporating the uniform distribution into deterministic programming language, we can express a huge variety of probability distributions. For example, we can use an if statement to define a Bernoulli distribution by checking a random number against a threshold. We can use the Box-Muller transform to define a standard bivariate Gaussian distribution by transforming uniform samples. We can sample from restricted regions of a space or from low-dimensional curves in an ambient space, even when they have measure 0. And by using probabilistic branches, we can create mixtures that are supported on really weird sets. And so a natural question we might ask is, well, just how weird can a probabilistic program get? So for example, using recursion, we can write a program that samples points within the complement of this Cantor-Dust fractal, which is the cross product of the Cantor set with itself. But is there a program that samples from that fractal, from the Cantor-Dust fractal itself? We know that it takes up a measure 0 subset of the unit square, but that shouldn't necessarily be an obstacle. We just saw that we can sample on a curve. We can similarly write a recursive program that samples from the upside-down triangles that are punched out during iterative construction of the Sierpinski triangle. But can we write a program supported on the Sierpinski triangle itself, the parts that are not punched out? And at this point, you might be thinking that these questions seem really esoteric. So I'm going to start by connecting them to some practical concerns we might have as language designers and theorists. Then I'll make the question of how weird a probabilistic program can get a little bit more precise before presenting our main result, and then trying to connect it back to some of these questions, these motivations that I'm about to present. So why do we care about how weird a probabilistic program can get? Well, as probabilistic programming language designers, we might want to reason about the coverage of our automation tools or interfaces. Do they handle any program that a user could throw at us? And so we want some way of characterizing the set of programs that a user could throw at us. And as theorists, it's also nice to have a new representation theorem or characterization of the definable objects in some language that help you abstract away details of how the program was constructed when you're trying to prove things about programs in the language. So as an example of a design question that might be relevant here, consider the primitive distribution interface. So most probabilistic programming languages have some notion of primitive distribution, and if you want to add a new one, you have to define a sampler and a density function, or you have to satisfy some interface. And one example of that interface would be that you have to write some program that samples from the distribution, and you also have to write a density function. And usually the specification of that density function is type dependent. So if I have a distribution over Booleans, I want a probability mass function. If I have a distribution over the reals, I want a probability 101 density function, right? And a way that you can make that formal is to say that for every type, there's some base measure, like the counting measure or the Lebesgue measure, and density should be computing a density with respect to that base measure. Now, this specification is pretty common. It's the one that we have in Gen, for example, pretty much. But a challenge with the interface is that a user might come to us and say, hey, I'm trying to implement a new primitive, and I've written the sampler, but I really don't know what to do about the density function, because my sampler, for example, samples uniformly along this curve. And there is no density function. There is no sort of probability 101 style density function for this distribution, okay? Because the whole support is contained in a measure 0 subset of the plane. And so if this is our interface, we just have to send the user away and say, sorry, you can't write that function. And you might be thinking, are users really clamoring for the ability to sample from the McDonald's M? And the answer is no. But we have run into this issue in our lab when trying to extend Gen with probability distributions for modeling the poses and rotations of objects in 3D space. We wanted to add various primitive distributions over unit vectors representing rotations. But just like that curvy M, these distributions don't have densities in the standard sense. So we went ahead and implemented them anyway, but parts of Gen's design makes assumptions that are incompatible with them. So when you use them, you need to steer clear of certain features, which of course is not ideal, right? So we would love to fix the primitive distribution interface to cover a broader set of programs. And there are various proposals for how to do that. For example, in this wonderful paper, Praveen and Kenshan define a small language of base measures. And we could say that a primitive distribution needs to have a sampler, a density, as well as an explicitly defined base measure object, or something like that, right? With respect to which the density is correct. And this idea of explicitly storing a base measure is also implemented in Chad Scherer's measure theory libraries in Julia. And a different set of Hausdorff base measures with a slightly different interface was proposed by Alexei Radl and Boris Alexeev in an AI stats paper in 2021. So depending on how expressive this set of base measures is, the new interface will have higher coverage than our previous interface. But is it universal? Okay, if a user comes to us with a program, can we always tell them a base measure that they can go implement a density function for? Yeah. M is a type, so MA is a type of measures over A. You can think of it as a probabilistic program returning A.
Why doesn't the measure also?
Because we are thinking that we have a restricted type that characterizes base measures. Maybe it's a simple algebraic data type that says it's either Lebesgue or or something else. But I just want to leave open right now how this interface could be defined. Defining the base measure as an arbitrary MA is a kind of universal choice, but it's also very hard to work with. Like you can't, for example, take two programs that both have densities and divide those densities because they're with respect to totally arbitrary base measures. Right? OK, so if a user comes to us with a weird program, we want to know that our spec is universal. And that's one reason why a designer of languages might care. How weird can a probabilistic program get? But before we can answer that problem, we should clarify what exactly we mean by the question. So we should set some ground rules. What language features and primitive functions are we allowing in this language in which we're going to think about the definable probabilistic programs? So we're going to start with a deterministic simply typed lambda calculus with real vectors and booleans as ground types, as well as tuples and functions. The symbol C here is going to range over primitive functions, which we'll talk more about in a moment. We'll then add support for general recursion via this mu operator, which binds the name f for recursive calls within the body E of the function being defined. And then we'll add all the standard constructs for probabilistic programming, including the type m tau of measures over tau, the terms return, sample, and score, and the do notation inspired by Haskell for sequencing probabilistic computations. And at Popple in 2019, Matthias and Huot and Sam showed how to give a denotational semantics to a language with these features. And even though they use all sorts of fancy techniques to interpret the language compositionally, at the end of the day, a closed probabilistic term returning real vectors is going to denote some measure over the real numbers, or over the vectors in Euclidean space. So our question is just what can we say about the definable measures, the measures that lie in the image of this semantic function, okay? And the key factor controlling the answer to that question is going to be what primitives we let into our language. And so there are lots of sensible choices here. But for this work, we're going to assume that the primitives are all piecewise analytic under analytic partition, or PAP. This class of functions was introduced by Wanyol and his colleagues in a great NeurIPS 2020 paper. And we extended the definition to cover higher order and partial functions at a workshop paper last year. But to give you an intuitive sense of what's being included here versus what's being left out, all of the operations exposed by NumPy and Julia's math libraries and Haskell's numeric libraries, like all the things that you typically find in a math library, including special functions, fit this definition. And any program you could write that composes those operations using branching and recursion also fit the definition. But some examples of things that are not included are weird things like space-filling curves and indicator functions for the Cantor set. So we really are thinking about, what are the probabilistic programs that you could write in practice using the kinds of functions that libraries typically expose to users? And you could choose a more general thing. You could say all measurable functions. And we know what the answer to the question is if you allow all measurable functions, also from this line of semantic work by Matthias and others, which is that you can define any s-finite measure, which includes all probability measures. So we do want something a little more restricted to make the question correspond more to our day-to-day practice. Now, with this choice in hand, we have a more precise problem statement, which is when the deterministic primitives in our language are PAP, what can we say about the definable measures? So what did we find? Let me first state our main result informally. For any probabilistic program, oh, yes.
Could you remind us again what PAP stands for?
Piecewise analytic under analytic partition. So the idea is that you have a function that is made up of, that you can sort of partition its domain into countably many sets that are nice in a certain way. And the restriction of the function to each set is nice. Nice means real analytic in this case for the function pieces. And then for the set to be nice, it has to be you have to be able to carve out the set using finitely many inequalities. G of x is greater than 0, where g of x is analytic. So it takes a while to sort of think through all of the implications of that, and both of these papers are nice for doing that, but it applies to a huge number of functions. It's smooth, and it has a nice power series. It's equal to, that converges locally, and it's equal to the power series. Yeah. Okay, so our main result informally is that for any probabilistic program returning a vector of reals, its denotation is a measure supported on a countable union of smooth submanifolds of Euclidean space. So, for example, and we'll get more formal soon, but just for an intuitive example, this strange program that we looked at earlier, we can carve up its support into a bunch of different smooth manifolds, each colored differently in this illustration. Some of them are one-dimensional, like these curves, right? Some of them are two-dimensional, like these shaded regions, okay? And this program doesn't have a branch that says, like, in this particular case, just return a point. But you could imagine that one of the branches just always returned a particular point, and that would be a zero-dimensional manifold in this image, okay? And our result is that we're supported on a countable union of these manifolds. And by the way, manifolds can't cross themselves and things, so we have to divide this curve up into multiple pieces in order to handle this, right? Now, what we mean by supported on, informally, is that every sample that you get from this program is going to lie somewhere in these manifolds, but that alone is not that impressive, because we could have just taken the whole space to be the manifold, right? So what we also mean is that if you remove any area from one of the two-dimensional manifolds, or if you remove any length from one of the one-dimensional manifolds, or if you remove any points from the zero-dimensional manifolds, then it no longer is supported on that, right? So all of the area that we're including here is essential. All of the length that we're including here is essential. Now, you can remove length from a two-dimensional manifold, and that's fine. But you can't remove length from one of the one-dimensional manifolds, okay? So how are we going to make this result formal? We need a couple of definitions, and these are also, we were sort of turned onto this track by Alexei and Boris's paper, which also works with Hausdorff measures. So the Hausdorff measure is a way of assigning sizes to sets, just like any measure is, and it's parameterized by a dimension d. Now, there's a formal definition on the slide to show you that this can be made rigorous, but what you'll need for the talk is the following intuition. When d is 0, the Hausdorff measure is counting the number of points in the set. When d is 1, it's summing up the lengths of any curves in the set. When d is 2, it's adding up the areas of the surface areas of any surfaces in the set. So for example, this little set A, that's this combination of two curves, has infinite zero-dimensional Hausdorff measure because it has infinitely many points. But it has a finite one-dimensional Hausdorff measure, which is just the arc lengths of the curves summed together. And it has 0 two-dimensional and three-dimensional and four-dimensional and five-dimensional Hausdorff measure because it has no area or volume. Whereas if we look at a set that does have area, then its Hausdorff measure is going to be infinite in the 0 and one-dimensional cases, finite for the two-dimensional case, it's just going to be the area there, and then 0 going forward. Okay? So that's the intuition of what this Hausdorff measure is doing. Building on the definition of Hausdorff measure, we're going to define a class of measures called s-Hausdorff measures. So this thing mu counts as an s-Hausdorff measure if, when given a set A, it spits out a sum of measurements of sizes, one term for each dimension from 0 to n, okay? And it's intersecting A with a different set in each dimension. So there's part of A that it's going to look at and count its one-dimensional volume, part of A that it's going to look at and count its two-dimensional size, three-dimensional size, zero-dimensional size, and so on. And these regions that determine which parts of the space are counted in terms of length, or counted in terms of area, or counted in terms of volume, are themselves countable unions of smooth manifolds of the right dimension. So, for example, we could take the support that we looked at earlier and the way that we divided up this support and use it to define a particular s-Hausdorff measure. And the way we would do that is we would set M1, the set M1, to the union of all the curves. And we would set M2 to the union of all these shaded regions. And what we would get out is a measure mu that, when given a set A to determine the size of, sums together two things. It sums the length of its intersection with the curve with the area of its intersection with the shaded regions. Yeah?
Does the Hausdorff measure coincide with the Lebesgue measure on the d?
It does. So if you're in Rn, then the n-dimensional Hausdorff measure coincides with the Lebesgue measure. And some authors define it differently, but we included a scaling factor, as did the Alexis and Boris's paper, to make it equal the Lebesgue measure. Yeah. So mu is going to measure a set in the special way determined by how we've decided to carve up a space into smooth manifolds. And so using this, we can give a formal statement of our result, which is that if we have a term of type mRn in our language, then there exists an s-Hausdorff measure, mu, for that term, such that whenever mu assigns measure 0 to a set, so does our program and vice versa. Whenever, and this is kind of implied by that, but whenever we have greater than 0, it's also greater than 0. And then this last part is important when your measure is not sigma finite. I'm not going to go into detail, but I'm happy to talk to people about it afterward. It's related to a condition that has been previously defined for this notion of 0 infinity absolute continuity. But just to give intuition to unpack this, remember that when we say there exists an s-Hausdorff measure, what we're really saying is that there exists a choice of these m1, m2, m0, where there exists a way of carving up the space into unions of manifolds of each dimension. And when we say mu e of a, we get that what we mean is the total size of a as measured on each manifold. And this term over here means the total probability or measure of a under the user's program. So what this is telling us is that exactly what we said informally before. Anything the program assigns mass to is part of these manifolds, and every part of these manifolds have some probability of being hit by the program. Okay? Now, I'm noticing that I'm running out of time, but we can use this in order to go back to our examples and establish that no, we can't write a program that samples from the Cantor set or from Cantor dust. And I'll talk more about that with anyone who's curious about it. I just want to very quickly say what this means, going back to our density interface. So this was our theorem. It implies that every program E has a density, rho sub E, possibly, and it's allowed to be infinite at certain points, with respect to this measure mu E, this special s-Hausdorff measure mu E. And not only that, they're essentially unique. So if I have two s-Hausdorff measures, and they both satisfy this thing, then the densities with respect to each of them are E almost everywhere equal to each other. So we can kind of write rho sub E, meaning the density of a program, and mean something basically unambiguous or essentially unambiguous. Just like with a normal density, densities are only defined up to a measure 0 set. S-Hausdorff measures can be divided. So if I have two programs and they have the same support, they're mutually absolutely continuous, then I can divide their two S-Hausdorff densities and I get their radon-Nikodym derivative, or their density ratio. And if the absolute continuity only holds in one direction, where one program support is contained in the other program support, then I can basically divide the densities, but I have to multiply by an indicator function. And what this indicator function is doing is it's basically doing what has been previously proposed in Alexis and Boris's work, as a dimension check. You might have seen this come up if you've seen the paper on the Indian GPA problem. So this suggests that we could have some kind of distribution interface based on s-Hausdorff measures, where the density that we use is actually this s-Hausdorff density instead of the standard density. But we'll need something else in there to help us do the dimension check. And this base measure problem in its solution paper at AI Stats 2021 that I've referred to a few times gives a nice interface for implementing that kind of thing. And what our work shows is that it really is a general solution. It doesn't leave any programs out if your primitives are PAP. We also show that we can divide these densities soundly to get importance weights up to a dimension check. And we haven't talked about it today, but it extends to program that returns lists of reals with no maximum dimension. So even if you're not just in Rn, if you have a program that every time you run it samples some different number of numbers, you can still talk about the s-Hausdorff densities. So in conclusion, we asked what the posteriors of probabilistic programs looked like. We gave this answer based on being supported on countable unions of manifolds that has interesting implications for designers of PPLs. We would love to explore efficient implementation of these designs that are suggested by this, as well as compositional automation of the computation of s-Hausdorff densities for programs. Thanks.
Thank you so much.